All right, so yeah, we're gonna go into like I guess section 24. We'll review parts of it. There's a lot of different kind of like, to be quite honest, a little bit of like kind of stuck together stuff in section 24. I know you all are going through the next like into the next project. I will kind of emphasize is that that most of the material that you need for that project is really, I'm just kind of looking on the side here, like really like section 20 to like maybe 22. So if that kind of makes you feel a little bit more at ease and being like what you need to understand. I think if you really were to focus sections 20 and 21, you'd have pretty much most of that project like understood. There is some SQL aspects too if you guys already looked at what that project looks like and everything. So just kind of know this is some extra stuff as well. Like resampling and Monte Carlo. I really would love to talk about Monte Carlo because I think the curriculum doesn't really talk much about it, and I don't know, it's kind of like my, I like the subject, so I think it's one of those things that a lot of data scientists might not have as much familiarity with, and honestly it gives you a little bit of extra competitive advantage understanding a little bit like what Monte Carlo is, and that's a available or a viable part. As always, that repo, the GitHub repo, you can check that out. I think I sent it yesterday too for you guys to check out. So that's in there. So we must look at probability statistics. And I'm going to try out a new thing today, ultimate hopscotch. And we'll see if we can get to that because that's kind of, I think it's a little fun little activity you can do. So some quick stuff about data generation. So some stuff about here, the curriculum kind of mentions about data generation, like what this looks like. So the reason why we actually would generate our own data, like basically think like not real data, right, is basically to test out a lot of our, what's called our algorithms to see, how well these perform. So in the future, as you collect more and more knowledge, especially different machine learning algorithms, and you might say, well, okay, like how well does this perform our data? And it turns out that different algorithms will perform differently. So this comes actually from sklearn's documentation, and it doesn't really matter. We haven't talked about any of these stuff, but you can look on this column section. Each of these are different classification algorithms. So the idea here is if you have the little data points which are on those squares, the idea is like we don't know what those in these algorithms, they don't know what group belongs to what, and they're trying to identify what groups are most similar to each other. And you can probably guess, like looking at like a data set like this, like it probably makes sense that this outer circle is more similar to this similar circle. So that should be two different colors, basically two different groups. And same thing with this kind of like this we call these like moons, but like this like half moon, crescent moon shape right here is basically like, well, this should really be one group by itself versus this group. Versus this very bottom one over here, you can tell it's not really make sense for them to be in any one particular group. And so what's nice about data generation, we can basically create very quickly random data without ever doing this and test out our algorithm or test out our classifier and our different points and see how well it performs. So you can see here is that depending, like this algorithm right here does a pretty decent job, it looks like, for like maybe this data set. Like it's a little bit of fuzzy right here. It does really well. All of them do really well on these like very individualized kind of like isolated points, but you can see some differences going on here. And this allows us to kind of like say, hey, throw some data at it and say, hey, how well do you perform on this kind of data set? And this allows us to kind of do some little quick testing and stuff. And it's super useful in that way. And again, one thing I'll note, it's quick. We don't have to go collect data like this. We can say, well, especially if we assume like, oh, our data is going to look like, this kind of section or more like these oblong shapes, we can say, oh, we know the data likely looks like this, so we can generate more data and see what that looks like. So this is kind of like why it's useful. Does that make sense to everyone? Cool. All right. So I'm just going to quickly go through some review because I think for the most part the curriculum kind of shows this part, but I think we kind of see a little bit like what's going on. So some quick coding examples. I'm just defining some functions here in our different groups so we can color them a little bit so it's a little easier to tell. So for example, the first one is just making blobs, and like blobs literally looking like little points like this. So you can see kind of similar would be this group over here. And note these are all random. So if I actually rerun this again and then run it, you can see it making different blobs. And each of these yellow, blue, red, green, those are just different groupings essentially. So different classifications. And note that I can basically generate, very few. If I want just like, let's say 60 of them to test out, I can do that and say, okay, here's 60 different points with this many different centers, meaning 4 different groups. So that's why I colored them out so they're a little bit easier for us to see. And then also features. So for example, this is only a 2-dimensional part. but you could potentially have this for 3, 4, 5 dimensions, right? And different features, and basically have it random. And the idea with blobs, it makes it so it's kind of like a more clustered area. And so in some situations, you might want data like this. Okay, make sense so far? Pretty straightforward. So you'll see very similar stuff. Basically, if you can understand how this is generated, you can see basically you're going to have something very similar on this side. So this case, we're going to make moons, right? And you can see here a little bit of this kind of moonish shape. And note that I have this noise factor. If I decrease the noise to let's say like 0, you'll see that our moon shape looks perfectly like this. And so this noise factor allows us to say, well, you know, no data probably looks like this. Like this seems either very precisely corrected or probably just overfit in that sense. So it's nice to kind of add this extra noise part where I get a little bit of fuzziness in this point. Note that if I put too much noise in here too, even though it's going to based on those different intersecting moons, you actually get a lot of overlap. So you can see 0.9 basically, like, I don't know about you all, but like I cannot easily tell, oh yes, that clearly comes from a moon-shaped data set. Even if I were to increase it probably to 500, I think it still would not be super clear, but it might be a little clearer. You can kind of like, if you knew it was a moon, you could probably reason out, but this is where you can see the different noise and stuff like this. So it's a nice little factor to go through. Note that there are other parameters here as well. For example, the shuffling and random state. Random state, for the record, it's always a good one to actually put in if you're generating data, just because then it makes it consistent and you're not generating data and keep generating data to find something that works well. If you put a random state, that's equivalent to just saying, okay, this is my random data and that's consistent for every model. So if you imagine rerunning this over and over again, it probably wouldn't be a good idea to like have a different random state each time, because you basically are going to start fitting us different ones and might just by pure chance fit better than normal. So good practice, always set your random state if possible. Okay, cool. Next part, like making circles. So again, this is just from the curriculum, and you can see here, these are kind of like intersecting, or it's not intersecting, concentric circles. So you can see here, if I put like small amount of noise, you can see that it looks basically like these circles right here. And then as I increase the noise, as we saw, this becomes a little fuzzier exactly where it goes through. And again, this just depends on what kind of data set you're looking at. Okay. Cool. The next one, this one I really like, is making regression data. So this can be really useful when you're trying to find a regression. Like, you know, I use this all the time when I'm trying to do demonstrations of like, you know, like how you fit like a different model on regression lines. You essentially can just use this make regression. I like to use like little, sometimes even just making norm, just I'll write an equation and just put in those points and then add a little fuzz to each point. But this essentially does it for you, so you don't have to worry too much about you creating the equation, going through and all this stuff. And again, there are a bunch of other parameters you can do here. Okay. So again, quick ways for us to make data. If we wanted, for example, though, like say, hey, my data isn't going to look like a line, it's going to look a little different. Like let's say we expect it to be like quadratic or cubic kind of function. We can take this data from a regression line and just transform it within here by passing it to different equations. So for example, here I have y2 taking this y data, which was from the regression points, and just basically transforming it in this case with y squared and y cubed. And I put in a little alpha here for us to better see it. But you can see these two different plots now where we have more of a quadratic form right here. And again, randomly distributed, and our cubic function right here. So again, this allows you to basically form whatever kind of function you need for whatever thing you want to test on. Okay. Sound pretty good? Any questions on data generation in general? No? All right, cool. Note there's other ways you can kind of like talk about generating data. One thing, besides just, what's it called? Generating data for like, okay, so like, let me ask you all, like if you had a bunch of data, like would you ever need to generate any data? Is there any scenario like when you would actually need to make data, even if you had a lot?
Yeah, so with regards to data, and I'm just shooting in the dark, but you might still need to generate more data as a means of testing, because if the data you currently have is what you're trying to analyze, you don't want to build your model off of it, or else you can overfit your model to the data you currently have. So a better means would be create test data, see how it works on that, try to get a good fit, add in some noise to see if you can improve the results. then use that trained model on the data you have.
Yeah, this could gotta be used like validation, right? So like this is something that's separate from your data that it's trained on or something like that. You probably wouldn't necessarily want to train it on this data set because then it's not going to be realistic of like what the real data you have. Another aspect that you might want to consider is like if you have rare events that come up in your data set. For example, I know like I was talking with some data scientists from Uber, and one of the big part that they have for their self-driving car unit is they want to make sure they do well on parts that don't occur very frequently. So for a self-driving car, you can imagine, it doesn't happen frequently, but someone might, intentionally jump in front of the street or in front of a car, ideally Uber does not want, or any self-driving car does not want to hit that person. They want to avoid that part. But if they collect all this data, it's very unlikely for them to see those kind of events, but they're really important things for them to do. So they actually generate this data and say, what would that event look like, and generate a lot of random data. And they will actually train on those kind of rare parts, or at least if they have other cases where they've seen an event happen before, but it only happened like once or twice out of like, millions of times they've done this experiment, they might try to emphasize that point and basically kind of generate other data points that were similar to that, but with enough fuzz, right? So enough extra part. And this also helps a little bit of what more like data augmentation, which is kind of related to this data generation. So just kind of know like that's kind of a few things. Obviously, what I just described is a little more advanced than what we're showing here, but for the most part, this can be really useful for like validation and just testing out like, what happens if my data is a little more extreme? What if my data looks like more of these elongated parts, or, these crescent moons is a really classic one for classification, where you might have data set, but you can see a lot of algorithms do very poorly on doing that. And also note that like even some algorithms with just random noise will find patterns in them even though they don't exist. Okay, sound good? Cool. All right, so this is going to be our data topic section, right? So next parts are resampling. So resampling is an interesting one. Kind of fun fact, I was kind of like, when I was first going through this notebook looking for like examples of resampling between Bootstrap and Jackknife, I actually found like my old professor's was one of the first results about bootstrapping and Jackknife, which I realize now it's not loading too quickly. Maybe it's too big, but it's a great little paper that he wrote in here. There it goes. That kind of goes through a whole bunch of like mathematical reasons, like why you might use Jackknife versus Bootstrap and stuff like that. For the most part, though, bootstrapping tends to be much more common than Jackknife. Jackknife can be more computationally inexpensive, but it's a lot less common now, especially with more advanced computers. Bootstrapping is kind of like, you might as well just do that. So just know that people tend to do bootstrapping over Jackknife, but it's important to know what those different things are. So just know resampling means that we basically take subsamples from a sample. So we might have seen this, I'm trying to think if you guys have seen this before, but this might be for like the central limit theorem, where you have a sample and you resample over it. And if you resampled over it with replacement, right, you will see that you will get a normal distribution from this. Okay? And that's mostly probably using from Bootstrap itself. So one thing you can kind of imagine here is like we have some random sample right here, which is in this case, it's about 1 point, something pi divided by 3. And then just have some extra points right here, normally distributed around that 1.03-ish, whatever this value of pi divided by 3 is. So you can imagine to have some data points with where I really want this point, but that's like the average. But it's just being kind of muddled with some noise. So bootstrapping allows us to kind of like randomly sample on the sample. And so if you wanted to do this, essentially what you can do is just do a random choice on here. And this is essentially going to pull right here. Each of these parts are going to be sampled with replacement in this case. And that's what bootstrapping is. It's with replacement. The way I kind of describe this is like, if you have like a hat of like names and you pull the name out, and you're like, oh, cool, it's Victor. All right, cool. And you stick the paper back in and you shuffle it up again and pull up another name. It's like, oh, look, it's Andy, and put it in there, and you shuffle it again and you pull out, oh, it's Victor again. You have that basically resampling. And that's essentially what Bootstrap is doing. So this is resampling on this, using this choice, basically choosing a certain size from this random sample, and then note that replace equals true. So this is one way to do it. An alternative way with scikit-learn here, instead of NumPy, you can use the resample part. And this will do a similar thing where if you run this right here, you can see it resamples over many parts. And this allows us to, this allows us to resample our sample and basically create new parts of it that are similar, hopefully, to the original population of that sample. Okay, does that make sense to everyone? Yeah, cool. Yeah, so this again can be really useful for us to actually like perform tests on here, or decide like what does the population really look like and things. Jackknife is an interesting one, and I think for the most part people get very like, what? Like, why would we do this? But Jackknife basically is that you make new samples. So if you imagine if I want 5 samples from Bootstrap, I would basically rerun this resample 5 times, and that will create hopefully 5. Well, it will create 5 new samples, Bootstrap samples from the original sample. Jackknife does a little something different, where basically it creates samples by removing 1 or more of the observations at a time. So if you imagine I have like 10, like if I have, let's see here, I'm going to just draw this out. There we go. So if you imagine I had like the numbers, let's say 2, 3, 5, and let's say 4. Okay, in that order. If I did something like Bootstrap of like this sample, I might get something like 2, and then 5, and then like 2 again, and then like 4, right? And then I do it another time. Oh, I get like 3, 5, 5, and then say, oh, I get a third 5. So like, you get some random with replacement. Jackknife will create a subsample, basically saying, okay, let me just remove 2. So it'll be 3, 5, 4. The next sample will be 2, 5, 4. The next sample would be 2, 3, 4. And then you can imagine the last one's going to be 2, 3, 5. So you can basically, it's just removing 1 of those points out here. And I think this is where people say, like, why would we do it this way? And the idea here is like, well, it turns out this is actually relatively computationally efficient, because now we don't have to randomly sample. Like, imagine essentially to do Bootstrap, you essentially have to take the hat and pull 1 out from the hat, put it over there, put it back in there, pull 1 out, write it down, put it back in, shuffle, put it over there. It takes a process on the computation. Where Jackknife, you can say, hey, just get the list of things and just don't use this one, and that's your sample. So it turns out it's relatively simple for that, and it's computationally efficient. So this can actually be really useful for simulations, and especially for Monte Carlo, it turns out you don't actually need to have it randomly sampled. You can essentially just say, hey, I sample from this sample, or the sample, random sample from my sample, it's just removing 1 point, and that will actually perform similar variance and similar kind of mean. And that's actually, if you're curious, that's what this PDF kind of talks about, is saying, estimating that error and stuff like that within using Bootstrap versus Jackknife. And it turns out Jackknife can do just as well. So it can be useful for applications where you have to do many, many, many simulations over, and it's just more computationally efficient. Just say, hey, just use essentially a Jackknife over a Bootstrap, where if you did a Bootstrap of like, if you imagine this resample, if I had a huge thing of like, let's say 10 million, points, right? I now have 10 million samples by just removing 1 point on each one. Versus a Bootstrap, if I wanted 10 million samples, that's going to be computationally efficient. I essentially have to sample over that over and over again. Okay, so kind of showing what the little example is. Kind of wrote a little code here. This is kind of similar to the lab that you guys will do. But basically, I just say, hey, first part, last part, and just remove 1. Note that this is relatively inefficient for me to save this part. So this, if I run this whole thing, I won't go through the whole part, but if I were to run this whole thing and go through it, it can take a long time. I think in this case, I don't remember how big of this sample I had. It's like 100, 1,000? That might be small enough. But basically, you can pull this part out, and you can see all my different resamples here. I have 1,000 different samples, each with 999 points. So this was relatively quick, about 2 seconds, versus if I did Bootstrap, this might take a lot longer in the sense that it has to basically perform that shuffle every single time. There's some efficiencies you can do, but it still is technically slower. And then I was showing this part. I won't show it because it will actually take some time. But if you were to run this, you can actually get the same average total and actually find out like, hey, this actually matches pretty well with what we'd expect the random sample to be. So it's not too shabby. Cool. Right, any questions on Jackknife or the difference between Jackknife and Bootstrap? Yeah, pretty good. Cool, cool. All right, and then some last part, permutation test. I kind of put this off to the side here. I didn't even write any code on it because this essentially is like a way of doing hypothesis testing without ever actually doing the hypothesis like t-tests and stuff like this. Essentially what you do, you say, hey, I have two samples, A and B, right? And what we can do here is say, hey, let's go ahead and randomly sample across A and B and then see the differences between those two. And essentially we're basically creating many samples over and see how many times does the average of A and B, the average of those A and B samples are greater than the other one. And then that basically can determine our p-value. Essentially, if we have a critical, if there are times where, let's see here, if there are times where A is greater than B, but it shouldn't be, that would be essentially our p-value. And they say, oh, well, that happens 2% of the time. Well, okay, that would be essentially a p-value of 0.02. So this is another way to do hypothesis testing. To be quite honest, it's not as common as you probably would just go ahead and do a t-test, but it's an option that you can in fact do. Okay. Any questions on any of this parts that I've talked about then? I'm pretty good. All right, cool.